Go ahead and start the recording then, since no one's jumping up to ask me anything. What I have in front of me, by the way, is an issue that came up in at least one homework so far. So I'm on the M+ website on their section for how to do the chi-square difference test for the MLM and MLR estimators. MLR is what we should be using here. And it describes how to do the test, but then at the very bottom, it describes a situation in which the test might go negative. So if that happens, here are some workarounds that they suggest, which is not covered in our course material. If that happens to you, please let us help you, and we'll see if we can come up with a different way of assessing the comparison of fit. For example, we had one student who added an error covariance, and that made the model fit better. So to demonstrate the improvement in fit, tried to do a likelihood ratio test, and it came out negative. That can happen because of the scaling factors. So in that situation, there is a hypothesis test for the error covariance already. The Wald test that goes with it, estimate divided by standard error gives you a z, which gives you a p. So you can report that as an indirect way of saying, because this parameter is significant, my model is fitting better. Usually you can do something along those lines of significance of individual parameters to be able to justify your decision to keep them. So that's this page that you can find on, again, the M+ website is not mplus.com. Apparently that was taken. It's statmodel.com. So I have this bookmarked. It's just easier that way. All right then, so for those of you who have not started homework 3, here's my advice. Don't wait till Monday night. It won't go well for you. There are certain types of homeworks that you could wait until Monday night to get started and do okay, but I don't think these types where you're doing individual analyses and making decisions and having to deal with amorphous situations is one of them. Tie into that, also don't wait until the night is due to start a grant proposal. So I'm rewatching the Grey's Anatomy series. Any other Grey's Anatomy fans in the house? A few people? Unfortunately. Oh, come on. This is a safe space.
I don't like that I'm a fan. But
yeah, I'm still a fan, and I will keep watching it until it goes off the air. Like, I've just committed.
Even if none of the main characters.
Yeah, none of the main characters there except for Bailey and Weber. They're hanging in there, but we're in season 20 now. But I'm on season 10 in my rewatch. And I got to what is the most improbable event in the 20 years of this series last night. So these characters, mind you, they are residents, surgical residents in a hospital in Seattle. All of them are very good looking. All of them have six-packs and perfectly curled hair and makeup at all times, despite the fact that they're supposedly working 100 hours a week and all of that stuff. And they routinely hop into on-call rooms to canoodle after a 10-hour surgery without so much as brushing their teeth. And they've had a mass shooter, a plane crash, electrocution, a tsunami of some kind, like all these disasters that happen, and somehow most of them survive. Not all of them, but most of them. But last night was the most unbelievable thing. So the main character decides that she's going to write an NIH grant. And throughout the afternoon, she's deciding which project she wants to do. And so then after dinner, she sits down to type out her NIH grant. And then we show her printing it off. And then she submits it that evening and then goes home to her husband and children. One night. And what she printed, by the way, was hysterical. It looked like an undergraduate term paper, like printing new livers from a 3D printer machine by Meredith Grey. And it was like double-spaced, like a typical term paper. So I was okay with that, like I laughed about it, but then you know what's gonna happen in the next episode? It's gonna be funded within a week. And the 3D printer is going to be set up within a few days with which she can print body parts.
Checks out.
I know. Does that sound legit to you? Like, that to me was the most unbelievable thing in the entire series that happened. Then, come on, Grays, do better research on this. So maybe Meredith Grey can wait until the 11 o'clock hour to start her grant proposal, but I would not recommend that for homework 3. How's that sound? Fair? Fair. Yeah, and apparently 3D printers are such not a big deal that my son's, one of his best friends, got one for his 8th birthday. So I guess you don't need an NIH grant to print body parts now. You can just like do it at home. So that seems convenient. I'm not up on the medicine, but you know. Yeah, so, yay science.
Probably need the grant to make it functional.
Could be. Could be, but if an 8-year-old can start printing toys.
Good body part,
actually
said you can
inserting a
print
body
it.
part into a body.
Yeah, it's nice to know that the surgeons can do it all, right? They have all the expertise to do all of the things, so. 3D printer icon, very nice, Zach. Anyone else have a 3D printer? No? I don't either. I don't even own a printer, I think, at this point,
I was
so.
gonna say, I think I barely own a printer.
I have one that works like inconsistently. You like hit it a few times, that kind of thing. But we don't need printers. We have electronic materials, right? And we don't need to do IRT by hand because we can get software to do it. So all these wonderful advances. So would you like to look at some results? Get back into our example? Sound good? All right. I'm going to anyway. So I will tell you in terms of things that are coming up, homework 4 will be about binary versions of these models as well as ordinal versions of these models. Depending on how far we get today and Tuesday, I might have to push homework 4 back 2 days. So that will be like 2 weeks. The next thing after homework 3 is a formative assessment. So I will let you know, but that's what it's looking like in terms of the timing of things. Let's see here. So the story for these data, these are real data, which is why they're not in the download folder. They are 7 indices of activities of daily living within a sample of older adults. And last time we looked at just descriptive information, so the proportions of people who are able to do each of these activities are relatively high. And we saw a difference in the type of correlation that's observed across the items when you do it with tetrachoric estimates versus standard Pearson correlations. Tetrachorics are going to be a better measure of association for binary items in particular. We looked at code. So let me highlight the things that make binary models different than continuous outcomes in terms of factor analysis and M+ specifically. Number 1 is this one right here. So categorical is the key option within the variable section. And categorical means binary or ordinal specifically. And you don't have to tell it how many categories each variable has. It will figure that out on its own. Otherwise, we're changing, I'm back to regular flavor maximum likelihood. I'm asking for a logit length specifically, which I believe is the default, and tightening the convergence criteria so that we'll get more similar results across different versions of M+. And I'm asking for some additional plot information that will be useful to us in understanding how the models work, as well as thetas, so predicted factor scores can be saved so that you can do descriptive kinds of things with them if you wish. And then the new part of the model is instead of intercepts, we have these things. Remember what the $ means? It's a threshold. What's an intercept versus a threshold? How are they related to each other? Yeah, they're additive inverse. I think of it as opposite, but that's probably not a specific enough math term. So if the intercept tells you the predicted logit that corresponds to a probability of 1, the threshold tells you the logit that corresponds to the probability of a 0 instead. So if I know that the probability is 0.9 corresponds to a logit of, let's say, 2, then the probability of 0.1 would correspond to a logit of -2. So if you don't like thresholds like me, then you can just multiply by -1 and turn them into intercepts. So then this is the factor analysis parameterization of the model that is estimated directly, where we get these factor loadings and these thresholds. And I have identified my factor by giving it a mean of 0 and a variance of 1. That way we can estimate all of the loadings and all of the thresholds. And by the way, the $, the 1 after it refers to the first threshold for that item. In binary items, there is only one threshold. But when we get to ordinal, there'll be $1, $2, $3, and so forth. You don't have to type this. This will happen automatically as a default, but I like to write out everything that's going to be estimated or constrained so that you can get a sense as to what to expect. So this would be considered a 2-parameter model, a 2PL, as it is known in the IRT world, 2-parameter logistic. 2-parameter ogive, is that a thing, 2PO? Do people say that? Not really. Or I would call it 2PP for probit, but you know, I can only say PP so many times without giggling, so we're just going to go with 2P. And in this model, all of the loadings are estimated separately. Another version over here is where all the loadings are set equal by writing this label as a single label for all 7, which creates a constraint. So give me a synonym for what this model is called. This is a Roche model, yes. So one parameter model or a Roche model. To me, those are functionally synonyms. The difference is in the method of identification. I believe a Roche model, A is 1 and the theta variance is estimated. So this is technically a 1PL because we're estimating a common A loading and fixing the variance to 1 instead. But 6 of one, half dozen of the other. And how do I know which one I should use? These are nested models, right? -2 log likelihood comparison. So we did that last time, looked at that at least. So the difference is treated as a chi-square with 6 degrees of freedom, so a chi-square value of 20. P-value is significant at traditional standards, so that means, yeah, I should probably let the loadings be different. Okay, got through that much last time. Any questions so far, or things you want to talk about more? Zoomers, we good still? There's some thumbs, all right. Okay, let's look at the numbers. So as I indicated at the end of class last time, 3 different versions of the model solution are given to you. They are all getting at the same idea through different parameterizations, meaning ways of expressing the model parameters and what is being predicted directly. So what is being estimated directly in the unstandardized model solution, or what I would call the item factor analysis version of this, are factor loadings and thresholds. So who is feeling brave here? And you can feel free to help read from the screen. 4.328 for item 1. That's a factor loading. Tell me what it means, please.
As the factor increases by 1,
Mm-hmm.
DI1 goes up by 4 point whatever units.
In logits, yes. So for every increase in the factor of 1, so that would be 1 standard deviation, given the way the model is scaled, the predicted outcome to the first item in logits, the predicted probability of a 1 in logits goes up by 4.3. So that seems like kind of a big number, but it's in logits. So logits don't really have, a scale to them per se. They range from positive to negative infinity. How about item 7? Who else wants to feel brave? Or copy what she said, either one. I don't care. Zoomers, you can play too. You can talk or type. 3.283 is the coefficient for the factor loading for item 7. You're brave. I can see it in your face.
As theta increases by 1, the factor scoring in logits increases by 3.28.
Yes, the predicted logit of a 1 increases by 3.28 for every unit of the factor. Now, if we look at the, and yes, Charlotte, good for you from Zoom. If we look at the range of these things, item 7 looks kind of like a bum item, doesn't it? Like relatively. These are all on the same scale because they're all in logits predicting binary items. Does that mean that I might want to consider dumping it?
No, and I'm a bit confused because I don't know how to quantify how good, like what 3.28 logit really means in terms of good or bad.
Yes, so that is very challenging in logit land. The way that this goodness would be expressed, I think more directly, would be via information. So each item has its own information function that describes how much reliability it contributes to the measurement of the trait at each point on the trait. And I think that might be a little bit better, but you're absolutely right in that this is sort of a weird metric that is not easy to talk about in normal English. But even if we accept that, should I call item 7 the worst item and then be done? Or is there more to the story? Because in CFA, right, we just went with like the factor loadings. Or their standardized versions, I'll scroll down here below. These are standardized factor loadings. You can think of them as the correlation between the logit of the item response and the factor. And so this one is still relatively lowest, even though it's quite high. Does this mean that this is the worst item and I may not need it?
Not necessarily.
Not necessarily. Yeah, what else do I need to add to my story here?
Difficulty?
Yeah, where is this item good? That's the question. And if this item covers a range of difficulty, or you can think of it as a range of subjectability in this case, that the other items don't cover, then I need it, regardless of how non-discriminating it is, because it provides information in a range which would otherwise have a hole in it. So we have to be careful about thinking about what is good and bad is not universal anymore in these models. It's good where, specifically. But in this case, it would be hard to argue that this is a bad item if the standardized loading is 0.89. That's still pretty darn good. All right, thresholds. Who's feeling extra brave? How about the threshold for item 7, since that's what we were just talking about? It's -6 approximately. Okay, you're feeling brave, go for it.
So since thresholds are for zeros, then I would say that in order for someone to have a 50% chance of getting item 7 correct, they'd have to have a theta of about 6.
That is the interpretation if this were a B difficulty. These are thresholds. And that's why you have to be extra brave, because this is very tricky. So you just told me this version. The item difficulties is computed. So what the hell is a theta? And I would agree that that version is much more useful, but what the hell is a threshold? The opposite of an intercept, right? So intercept is the predicted outcome when x is 0, right? That's the definition. So an intercept would tell me the predicted logit of a 1 when x is 0, which is your trait. So then this is the predicted logit of a 0 when x is 0. So an average person, with respect to this latent construct of ability, would have a logit of a probability for item 7 of -6. So putting that all together, and I apologize for the reverse negative, they are very unlikely to not be able to do the task. That's what this means. They have a logit of failure of -6 at theta equals 0.
So it's an easy item.
So it's an easy item. Yes. So the thresholds, even though they're backwards, the reason they're backwards is because they really are arranged in difficulty, where higher values indicate more difficult items. Higher values are consistent with a greater probability of failure in thresholds. And lower items like this one are a greater probability of success. So a person of average ability would have a very low probability of a 0 for this particular item.
So then that's where thresholds actually kind of do make more sense than intercepts.
Arguably, thresholds make more sense than intercepts, but the double negative just hurts my brain. So the way that I think about this is that like these numbers are a profile for what you can expect for failure for the average person. Like a theta of 0 gets you these. This person is unlikely to fail at any of these items. She's like, I'm waiting for you to say something I can write down. That's the best I got. At a theta of 0, these tell you the logits of failure. They're all negative, meaning the logits of failure. I am failing at logits. But it is what it is, unfortunately. And now you'll know why I don't like this, and I like the IRT version better. If we go over to the IRT version, which is what M+ gives you, the discriminations, these are your A's. And if you compare across the page, 4.3, 4.9, 4.3, they are exactly the same. Not a coincidence. If your trait has a variance of 1, then loading and A are directly the same number. So it's the slope at the 50-50 mark in probability. Hi. Okay, this is a first. My smart board just decided it wanted to reconnect itself while my laptop is fine. Okay, it's back. But we're gonna make it work, it's fine. If nothing else, I'll just turn this monitor around and you can watch the TV. Make it work. So yes, discriminations and loadings are the same thing. They tell you the maximum slope at the probability of 0.5. And it's a linear slope if you're predicting in terms of logits. Item difficulties, this is a rearrangement of thresholds. In this parameterization, it is computed as the threshold divided by the loading, I believe. Let me check my own memory of this. Yep, there it is. So I have the conversions for the theta method of identification, which is what we're using on slide 7 of lecture 5B. B is the threshold divided by the loading, and this part goes away if the theta mean is 0, and this part goes away if the theta variance is 1. So it simplifies the conversions in that case. So these are new information. These are, I would say, inarguably more useful. So even if you're fitting these models in software that uses a factor analytic parameterization of intercept and loading, arguably I think you want these two. These tell you, say it again.
Are these ones still threshold?
These are difficulties. Okay, so say what you said before
So
for item 7.
for someone to have a 50% chance of getting item 7 correct,
Mhm.
they would need a theta of -1.8.
That's exactly right. So these are the theta estimates needed to hit a probability of 0.5 in this model. More colloquially, that's a hard word to say, these tell you who the item is for. That's the way I think of it. Like, what kind of person is this item going to be maximally useful for in terms of the location on the trait, and then the slope at that point tells you how useful it's going to be at that point. So all of these are negative in this case. So is this a relatively easy set of items or difficult?
Easy.
Easy, yeah. So the fact that I don't have any items for somebody with a theta above 0, that is going to have a significant consequence for how reliably I can measure people with high ability. I can't. They can do everything. So we'll see that in just a moment. The rest of the page here, zooming back out so you can see, I took the parameter estimates from the item factor analytic parameterization and computed predicted probabilities given theta of 0 in logits here. So note that I turned these into intercepts by removing the minus sign. So these are now, they were given as thresholds. I reversed them to be intercepts so that I could write it in the slope intercept form that you often see in factor analysis. If I do the same idea, putting in the IRT parameters instead, so A goes outside the parentheses here, times theta minus difficulty. So I'm keeping the minus signs in here to highlight the fact that it's already minused. We don't have to turn it around like we do in intercept. You'll see that the predicted probabilities for the same level of theta are exactly the same. So at the end of the day, what this model is doing is predicting the probability of a 1 response or a 0 response given any item for any person. How it gets there is the difference between IFA and IRT. IFA is loadings and intercepts or thresholds. IRT is discriminations and difficulties. Okay, how are we doing? Now picture time. Pictures are much more interesting than tables of columns. So I made all of these pictures by exporting information from IMPlus into Excel. So the Excel spreadsheet that goes with example 5 has written instructions for how to navigate through the menus to do that. If you're fitting these models using MERT or something like that in R, you could also build your own. I'm sure there's packages or add-ons to that that allow you to compute information and things. But let's look at each of these pictures because they each tell a slightly different story. So the first here on the top left is item characteristic curves. So I have theta on the x-axis here, and a reminder that this is a standardized latent variable. I have the probability of a 1 on the y-axis, which is why these lines are bendy. If I had logits as the y-axis, what would these lines look like instead?
Linear.
Linear, straight. The model's linear in the logit, non-linear when you back translate the predictions into probability. So the location on the x-axis corresponds to which item parameter, A or B? Yeah, location is B. So these curves, like where they are, is given by B, or the threshold. How steep they are at that point is given by A. So item 7 here that I picked on earlier is relatively shallower than the others, although still pretty darn steep, but it covers an area that the others don't. So if you want to be able to measure very low people, minus 2 standard deviations or so, it's the only item you've got. So even if this discrimination were nearly flat, you would probably want to keep it because this is your only shot at differentiating amongst lower people, whereas the rest of these are fairly clustered in the middle. And this plot also highlights that maybe the 2PL is overkill. Like some of these lines look awfully parallel to me. So maybe we could have like a 1.5 PL. Can we make that a thing? Where some of the loadings are constrained and some of them that want to be different can be different? There's no reason we can't do that. It doesn't have to be all or nothing. You just need to find software that will let you do it. But all of these, though, if we look at where a theta of 0 is, they're all pretty much done at that point. So we have literally no information that would discriminate people of above average abilities from these 7 items. And that is shown directly if I were to plot test information, which is computed using the A's and B's for each item and then summed across items. So this is literally the amount of information these 7 items contain with respect to the trait. And it has a weird metric to it that most people don't know what to do with, myself included up until a few years ago. I will tell you that information of 30, which is where this peaks, corresponds to a reliability of 0.97, the way that M+ computes it. But then you have this drop-off right here. And you can compute reliability out of this by converting it from information divided by information plus 1, and it looks like that. So the way M+ computes information, by the way, adds in the part that's due to the prior of theta, which is why it stops at 0.5. Because information, the lower bound of it, the way it's computed is 1. So the worst reliability you can have is 0.5. So this is kind of like optimistic. But still, the story is the same, but most readers would understand a reliability coefficient as your y-axis. So this is good or bad? What do you think?
Depends on what you want to do with the test.
Yeah, so if I want to measure people that I'm worried about whether they can live independently and I might want to have them move into assisted living or get an in-home helper or something, this test, not too bad. If I want to measure highly functional adults, not so much. So if I wanted to measure highly functional adults, what would I need to do? Yeah, I'm going to pause that question because I've got a question from the Zoomers. Okay, let me answer your question while everyone else thinks. Zach, go ahead.
These graphs are for IRT. Is that true?
These
They
are,
correlate to the
they are
IRT
using
models?
the IRT parameters, that's right. Yes, okay, so how do we fix it? If we want to measure people of higher abilities, you were going to say?
Like items with more difficulty, or like items that are harder to do.
Items that are harder to do. So let's look at the items again. Housework, bed making, cooking, shopping, getting to places, banking, and using the phone. How about Zumba? Marathon training. Going up and down stairs. Stuff like that. Yeah, you can think of ways to extend this scale. Now, there's arguably sort of a mental component and a physical component. This could potentially be multidimensional if you wanted to organize it that way, but this is often used as one sort of composite deal. So yeah, these 7 items are great at measuring low ability people, not so great at measuring high ability people. So this information function, which summarizes the patterns of A's and B's, translates into this theta distribution. This red line's right here, that's my theta distribution. What do we think about that?
This assessment is not good for this sample.
It is not. So what distribution is theta supposed to have?
No.
Supposed to be normal. Does this look normal? No, it can't be. There is no universe in which these people who all can do everything are going to spread out with this test. It's a function of the instrument itself. So IRT can't save a bad set of items. It's not magic. And neither can factor analysis for that matter. So theta is supposed to have a mean of 0 and a variance of 1. The mean in the outputted thetas, so that's what this is. These are EAP estimates, expected a posteriori. This is the expected best guess, the middle of each person's distribution of what theta could be, where the standard error around theta tells you how wide each person's distribution would be based on their factor score. And the variance of these outputted thetas is only 0.74. So we call that shrinkage, usually. When you have relatively few items, the prior has more of an influence, and everything sort of gets pushed towards the middle. So we wouldn't be able to get factor scores at all for this pile of people who are at ceiling unless we used some kind of prior distribution. With straight ML, it's not possible. So the factor scores do not have the same characteristics as what they would if they stay latent in the model. Here's some other plots. So this is a plot of the difficulty of each item in the order in which the items were numbered. We can see that item 7 is by far the least difficult. That one was answering the phone. Here are the item thresholds. So these tell you the predicted probability in logits of not being able to do these items for your average theta person. And those thresholds translate into these probabilities. So there's different ways that you can describe this. I like showing B's, item difficulty ranges. I like showing these, and I like showing information and reliability. So pictures like this are especially useful when we get to ordinal to show how differentiable the categories are. That will be useful in scale development in addition to just how useful the items are as a whole. All right. Okay, how are we doing? Now the other game in town. How do I know if this model is any good? Here's all I have for fit right here. Do I have anything that tells me whether this model is actually fitting unidimensionally? All I have is the log likelihood for my model, how tall it is. I've got nothing to compare it to. It tries to compare it to the log likelihood for the best possible model, which is 2 to the 7 way contingency table of all possible responses, which we don't have enough people or information to fill out. So this is, while this is all useful, potentially, none of this is accurate if the model doesn't fit. So in IRT land, there are various limited information fit measures that you can use. What is it? RMSEA 2, M2, there's a few others that are linked in the slides. Here is an alternative that I want to show you and that you'll get a chance to practice in homework 4 and 5. So the same models estimated differently. So what we did in the first place was full information maximum likelihood, in which you get your choice of logit or probit as your link function. And that approach is best, so to speak, in that it uses all the individual data. It assumes missing responses are missing at random, which means conditionally random after you factor in the other information you do have. But that these first sets of models in full information fall apart real quick when you have lots of thetas. So after like 2 to 3, the number of integration points that you need becomes prohibitive, and it may not work at all. So for situations in which you have more than one factor that you're interested in, and you're not too worried about missing data, and you want to assess model fit using the traditional measures of CFA, welcome to limited information. And most of the time when people say item factor analysis or CFA with categorical indicators, this is what they mean. It's this version of the estimator limited information, WLSMV. Weighted least squares with a mean and variance corrected chi-square, I think, something along those lines. Do you remember what this is based on? We talked about it a little bit, I think, before break, so maybe not.
The summary statistics?
Summary statistics, yes. So limited information means we estimate a summary of the data first, and then the model operates on that summary. In this case, our summary is not going to be a Pearson correlation matrix like it would be in CFA. It's going to be some other kind that starts with a T.
Tetracore.
Yes, it's better to be wrong than vague. Say it loudly, even if it's wrong. Tetrachoric, yeah. So what this does is first use your data to estimate a tetrachoric correlation matrix. Then it tries to find the parameters that make that matrix the closest. Like it tries to make a parameters that make the predicted matrix the closest to the one it estimates. So this could go awry in the sense that not all of those correlations are going to be estimated well. One example of that I showed at the very first page. The tetrachoric correlation between item 4 and item 7 had a much larger standard error because it had an empty cell. Everybody who could do item 4 could also do item 7. Item 7 is much easier. So it doesn't really know for sure what that correlation should be. And so any of these correlations with relatively large standard errors, it's not really sure what it should be in the first place. It's going to downweight that in the estimation and focus on reproducing the correlations that are estimated more precisely instead. So that's the weighting process that sort of discounts the ones that it's not sure about to some extent. There we go. So to change to limited information, estimator equals WLSMV, parameterization equals theta. So there are two different ways to estimate this model in terms of how it's scaled. This one corresponds to probits. So in this model, the error variances are all assumed to be 1 in probits. In the alternative parameterization, which is known as delta, this is on a slide somewhere, the total variance is 1 instead. So all of the formulas that I gave you to go back and forth across IRT and IFA are specific to this theta version. You can get the ones for delta on the MPlus website if you so choose. And convergence equals this for comparability. Note what's not in here with respect to link functions. We had link equals logit before, right? Do you know what will happen if I try to add that? It'll say, nope, you're stuck with probit, too bad. So that's why I had to teach you probit, because I knew this was coming. You're stuck with it in WLSMV. So all of these estimates are going to be lower by a factor of 1.7 relative to the other solution, and they're based on a different method of estimation, so they'll be a little bit wiggly. Otherwise, the code is the same, although I am also making explicit what we're saying about the error variances being fixed to 1 in this case. This is a constraint needed for identification until we get to models that have multiple groups and we have invariance constraints across the groups. Then these can actually be estimated, although it doesn't often go well. Model fit information. Look, it's all back. It's back. Isn't it comforting? We get our chi-square tested model fit, 14 degrees of freedom left over, 14 free parameters. That's based on the number of items and the number of thresholds. It says, hey, by the way, you need to use this other method of doing likelihood ratio tests. You know why? Do you see HO in here anywhere? Or H1? Nope, doesn't give you log likelihoods because it's not really based in that. So instead, we have to make it do the model comparisons for us using diff test. I'll show you in just a second. RMSEA, this is familiar. This tells us what in terms of fit? Remember? It's like review time. Do we want this to be little or big?
Smaller.
Smaller.
About like how off you are.
how off you are from the perfect model, which in this case is the estimated tetracork correlations in the data as the answer key for what our model should be trying to reproduce with fewer parameters. And this p-value being 0.055 means we're right on the edge of what some people would call close fit in terms of testing against the null hypothesis of 0.05, or just on the other side of it in terms of the confidence interval. How about CFI and TLI? Do we want these to be big or little? Big. This is about as good as it gets. 1 is the cap for CFI. TLI can actually go above 1. Chi-square test of the baseline model. Do we care about that ever? Never, ever. This is the best possible model better than the worst possible model? And neither of those is your model. So if this is non-significant, you have nothing worth modeling, and you should pack up your ball and go home. Because the difference between the best model and the worst model is whether there's any correlations allowed whatsoever. And last but not least, SRMR, big or little? I'm watching you two Zoomers. I'm seeing your answers. Thank you. SRMR, do we want it to be big or little? Has the word residual in it? Little. Yeah, if it looks like it has the word fit in it, it needs to be big. And if it has some permutation of error or residual in it, it needs to be little. And this one, also pretty happy relative to conventional standards of 0.06, 0.08, somewhere in there is the high point. So yeah, it looks like this model is not too bad. I'll take it. What about the Roche model? What if reviewer 2 thinks I should have done a Roche model instead? Can I answer that using limited information estimation? Sure I can. Here's how I do it. So I highlighted in yellow the parts that you would need to change. A new command is save data. Diff test is the key word here. It does a whole bunch of computations under the hood related to derivatives that it says, don't even try, just do it this way. Don't try and do anything on your own. I said, all right, fine. And I'm saving the results from this model as 2p, meaning this is the 2-parameter model. Then coming over here and fitting the Roche version of the model, so 1 loading instead of 7, I then take what I saved the results for from the bigger model and put it under analysis. So the order is fit the model that has the most parameters, save the results from that to a file, and then fit a nested model with fewer parameters and tell it to go use those results to do the comparison. So this is not something you can compute by hand even if you wanted to. So then in your output for this model, I get 2 different chi-squares. The first one tests whether the reproduced tetracork correlation matrix matches the estimated one. The answer is no. But then this one, chi-square for difference testing. That's the analog to the likelihood ratio test. And so this tells me directly that there is a significant difference between the model with all the loadings being equal, which is this one, versus the model in which they're all separate, saving 6 degrees of freedom. And so therefore, the one with their separate fits better. Same conclusion as when we had the full information estimator. Is this thing still flickering? Am I going crazy? It's flickering. Okay. In my peripheral vision, I keep seeing something like flicker zoomers, and I'm like, am I that old? Is the rest of my eyesight failing? No. Yeah, the sad part is that I got LASIK. I could see well for several years, and then it started getting crappy again. So, I know. I thought I had fixed it.
Did it get bad in the same direction as it was bad before? Did it get
Yes.
bad okay.
Yeah, I was at like 2400 when I had LASIK, and then I was 20/20 right after, and then it slowly progressed. Now I'm at like 2100. And I went back, and my surgeon was like, you have 2 choices. You can get driving glasses, and I'll leave it alone, or I can try to fix it, but you're going to need reading glasses in a few years. So I picked driving glasses. So if I don't recognize you in the hallway, I'm not being rude. I literally can't see your faces. So no offense. I can either drive my computer and read this screen, or I can see you, but not both. So it's bugging me when it's flickering here, but I'm glad it's not me. All right. So same conclusion. The parameters that we get back are on a different scale. So previously, these numbers were all like in the 3s and 4s for the loadings. Now they're in the 1s and 2s. That's because these are probits. So they're off by a factor of about 1.7. We get unstandardized results, standardized results. We get the IRT parameterization in ogive. So this is the probit version, which I have reminded you down here. Same issue in terms of any one of these solutions can create the same predicted probabilities. So they're all doing the same thing. But here's the glorious part. Local fit. So in CFA land, what did we use to assess local fit? Remember this vocabulary? What is the idea of local fit? Let's start there.
Underestimating certain correlations.
Yes, it's a like point by point assessment of whether we are over predicting, under predicting, or right on. So local fit is essential in helping you figure out why your global fit is bad. Like where is the mismatch occurring? And in CFA, we had residuals in terms of a correlation metric that we transformed, they were transformed, I should say, into normalized or standardized residuals, normalized being the ones I prefer. And those were like z-scores for how far off. In WLSMV, we get this. Residuals for covariances, correlations, residual correlations. That's not a confusing label at all, is it? These are not error covariances or error correlations. These are offnesses in a correlation metric. So this is how far off each of my predicted correlations is between what the model says and what the data say in the tetrachoric correlation matrix. And I've highlighted the ones that are the largest here. This is under, so meaning these items want to be less together than the factor thinks they do. This one's a little bit under, but the rest of these are all pretty small. So in my write-up for this, by the way, because here's the words, because yay, we finished this example. It's so exciting. Go ahead.
So, for like how off things are,
Mm-hmm.
like is it a relative thing where you're looking like, oh, all of the other ones are smaller and like these are the bigger ones, or is it more of like an like is there a number that's like a general cutoff for it, or like where you should start being concerned?
So the question was, which is actually the point I was about to make, so thank you for setting that up perfectly. The question was, are there cutoffs for this in terms of where you would be concerned what's good enough or not good enough? So this tells you the offnesses without the weighting applied. So not all of these offnesses are equally precise. So for that reason, you would still want to look at modification indices to see which ones are being prioritized in terms of the estimation. But the answer is really no. Like I would say that I'm off in a predicted correlation of 0.1 at the most. Like I can live with that. And in my write-up to this, I had written that exact number right here, and you'll see that I took it out and put question mark here, so that when you use this template for your homework, you don't adopt this arbitrary standard of all the correlations were less than 0.11, and that's what makes it okay. Because I mistakenly provided that impression before, so now I'm fixing it. There is no standard. But you can say all of the offnesses are lower than this, and I can live with that. It would be very different if, like, I had a misprediction in a correlation metric of, like, 0.3 for one of these, and the rest of them were fine. Like, that to me is like, okay, I need to deal with this one. But these are pretty well scattered across, so I can live with this.
And does that also apply in like CFA with the normalized ones that we had before? Like there's not a specific sort of cutoff, it's just kind of looking at it and like, okay, eyeballing it for lack of a better.
Yeah, so the question was in CFA, when we look at normalized residuals, yeah, there's no real cutoff. Because they're in a z-score metric, you might be tempted to say, well, a z-score of 2 is pretty unlikely, so let's focus on that. But the reality is that those are computed using the standard error of the correlations in the denominator. That's a function of sample size. So if you're in a really large sample, you can have normalized residuals of 15 for things that are actually quite small because they're very, very precisely estimated. So it's still just relatively where are the holes? Like where are the biggest problems? And that would guide you towards how you might want to revise your model. Okay, so this is way more words than anyone would ever write in a results section. But because this stuff is confusing, I wanted to write down as much as humanly possible to describe the process and the estimation and all the vocabulary words. So you will have that if you're using binary data for homework 5. You'll get to play with these models for that. Most of you will be using ordinal data instead, so that will be the next example. But I believe we have just a couple more slides that I haven't talked about, so I can hit those on the way out, and then we'll actually be like on time. That means I have to do work over this weekend getting your stuff up by next Tuesday, but I can live with that. All right, let's see, where were we? Estimation, I'm not doing that again. No. Did this, okay, yeah, just a couple other ideas here. Differences in what you can and can't do. So this describes WLSMV estimation, what we just went over. The biggest issue to me in using it is this one right here. It's missing data. So if missing data is not much of an issue, I don't see a problem with this. There's quite a bit of research looking at how this compares to full information maximum likelihood, or CFA, and WLSMV works pretty well in a lot of cases, but this is the big one. Anytime that you summarize your data first and operate on that summary, you don't know how the summary was made. So that means you have to assume that any incomplete information is missing completely at random, which is what it sounds like. Like there is no reason why somebody didn't answer a question. Most of the time on a survey, though, people don't answer questions for reasons. Either it's the end of the survey and they don't want to do it anymore, or they don't want to answer that question about whatever sensitive topic you've asked them. So this is potentially a problem, especially if you're doing a longitudinal analysis where you have attrition at the same time you might have selective non-response. In terms of modifying the model, there are differences in what you are allowed to do as a function of estimation in these models. So this is slide 36 here. This will be the end of the story. So if you are using full information maximum likelihood, your model parameters are either loadings and intercepts or thresholds, or A's and B's, right? We're missing one more item parameter that we had in CFA. What else did we have per item in CFA that we don't have anymore? Error variances, right? What is error variance in these models? In Logits, it's 3 point something something, that's correct. Pi squared over 3, more specifically, from the logistic distribution. The idea that the continuous underlying distribution that could have an E has a variance of 3.29. In Probits, what is it? Finger question.
1.
Yeah, 1. So we don't have error variances. So can you guess what will happen in M+ if you try to make a covariance between a thing that doesn't exist and another thing that doesn't exist? You'll be like, what? No. So there's a workaround. So if you are in limited information, if you're in the world of WLSMV where you're working with correlation matrices, you can actually have error covariances, but not in full information. So here is an analog to how you can deal with this. So let's say that I have the WLSMV way here. I have a trait indicated by 5 items. My trait has a mean of 0. My trait has a variance of 1. Okay, good. Let's say that I look through my misfit in WLSMV and I decide that items 2 and 3 need to be extra related, so I add in an error covariance. Fine. Here is how I would do that same thing if I were in full information. The first part is the same. The second part is that I need to add what is known as a method factor or a specific factor and turn it into a bifactor model. There's going to be more on this coming, but this is foreshadowing how that works. I would create a new latent factor. I'm calling it error fact. That is only indicated by the 2 items that I want to covary. And I fix their loadings to 1, and I estimate that factor's variance, and I shut off that specific factor's correlation, covariance, with the trait. So this, oh, it wouldn't be a class if my computer didn't want to restart itself in the middle of it. Thank you. every single time. Let me get you a picture that goes with this, because in hindsight, I should have put in a picture, but I didn't. I think it is in part 2 of CFA. I know exactly what picture I want. 1 second. Is it part 1 or part 2? That's my only question. Oh, yep, found it. Okay. Un momento. Here we go. This is CFA part 2, slide 39. What I'm showing you is this option right here on the right. That's what we're doing. So we're having all of the items still load on one factor. We're creating a second factor that only has the 2 items that I want an extra relationship for as indicators, and there's no covariance between the 2, so I'm shutting that off. So this is called a method factor model, a bifactor model, or specific factors. Take your pick. And it is a way to do the same thing as adding in an error covariance. This new second factor induces another source of relationship between these 2 items in the same way that this error covariance induces another source of relationship between these 2 items. So then in the output, you would end up with this new variance of a factor that you can interpret as creating a covariance between the 2, although on a somewhat different scale. Ta-da! We made it. So the reason, by the way, why bifactor models are a thing in IRT is because of this constraint. You can't have error covariances. So any extra relationships you want for your items have to be done via factors instead. If you have a negative relationship, can you guess what I would do instead to create a negative correlation? Yeah, make one of these minus. Then the factor variance would create a negative relationship between the 2. So this will be relevant in when you're working on your own data. Those of you who've been working in CFA, how many of you have error correlations in homework 3 so far? Like everybody. Guess what? You got to do this instead in homework 5. You got to add some error correlation trait thingies. So, all right. So, questions? Things you want to talk about more or again? Okay, would you like 13 minutes to go work on homework 3 then? Or do something else with your lives? Your choice. All right, then I will wrap things up a little bit early. Let me or the TAs know if you need anything. Oh, we got one more question before we go. Can we please repeat why there is no error in IFA? Yes, because in IFA, as estimated via full information, error variances are not things. So because the variance is not an estimated parameter, covariances are not estimated parameters. However, in limited information, you can actually have error variance, so to speak, but it's not estimated. It's just fixed to 1, but that still allows a covariance between the errors in limited information. So WLSMV, in the same way that it gives you fit as in CFA models, it allows you the same model extensions of error covariances. Full information does not. So that's the one that requires a factor as a workaround. Okay, did that help? Excellent. Okay then, let me know, let us, the TAs, know if you need anything. I look forward to reading your homework after Tuesday. All right, thanks for being here. Have good weekends. Enjoy episode 2 of season 20 of Grey's Anatomy this evening.